Welcome back to your channel, FE Civil Exam with Farhad. Let's review an FENP sample question in fluid mechanics and hydraulics of pipes. So let's jump to an example in pipes hydraulic in terms of application of Bernoulli's equation in pipes. So we want to calculate the velocity at the exit of a combination of two pipes with different diameters and different length, mm, which they are attached to each other and their center line are at the same elevation. So we have their length, their diameters, and also the head loss. For example, for the larger pipe, which is 12 inches in diameter, the friction head loss is 3% feet over feet, and for a smaller one, the friction head loss is 5%, which makes sense. It's narrower, so the friction head loss is seems to be higher. It can also be due to the materials change. A and also at the contraction, we have like a 7 feet of head loss at the diameter change, which is the friction head loss due to contraction. We do know the length of each of them, and if we do know that the pressure at the entrance and the fluid enters and goes out is water. If we do know that the pressure at the entrance point, which is point A, is 80 pound square inches and the velocity at A is 10 feet per second, we want to calculate the exit velocity, which is V sub C in terms of feet per second. So let's jump to our solution. So this is the, if you go to the FE and P references for minor losses in pipes fitting contraction and expansion in terms of Bernoulli's equation, you can find the Bernoulli's equation includes the head loss. This is definitely the Bernoulli's equation, and at it can be found in the FE and P references and any fluid mechanics and references book related to hydraulics and fluid mechanics, you can easily find this equation. This is the Bernoulli equation. So Bernoulli's equation, it just says pressure at the first cross section. So if we just assume our entrance point is cross section A or 1, and our exit point is our cross section 2. So the first part of Bernoulli's equation applies for first cross section. The second part applies for the second cross section. So P1 over gamma, definitely gamma of water, plus Z1, which is the height of that from a point from a reference, plus velocity at the point 1 squared over 2 times over G. So you can easily consider, if assuming the center line of the pipes at each locations stand at each point stands the same, so definitely z1 with z2 simply cancels out. So our Bernoulli's equation, it just uh, simplified to this version, excluding the z, the elevation. And also we do know that at exit point we have free jet. At free jet pressure is 0, so this terms goes 0 P2 over gamma. So again, we can even simplify the Bernoulli equation. So the first part is left with the P1 over gamma plus V1 squared over 2g is equal to velocity V2 squared over 2g. We do know from the conversion table that 1 pound square inch is equal to 2.31 feet per water. And if you don't know that, we just jump to that one. So assume we have a columns of water with the pressure of 1 pound psi or 1 pound square inches. Convert it to feet. Each 12 inches is 1 feet, and then it's a squared. So just make it a square and divide it by gamma of water in US customary unit, which is 62.4 pound per feet cube. That's gamma of water. And if you cancel out the unit, it just gives you 1 psi is equal to 2.31 feet of water. It just says if we have a tank and we apply a 1 psi pressure at its bottom, it's equal to 2.30 feet of water, or vice versa. If we have a column of water with a height of 2.31 feet, the pressure applies at the bottom is 1 pound square inches. So as we do know this part, so again 1 psi is equal to 2.31 feet of water. Just be careful if your liquid change, it definitely should be divided by the gamma of that specific uh, liquid. It's just for water. So let's go back to our equation. So far we have our Bernoulli equation simplified and replace this term, the very first term, by the equivalent height of water. So Bernoulli's equation in terms of head loss, it just says the water enters at point A, passes through a pipe A. It has like a friction head loss due to this length times to this coefficient. Then at contraction, there is another head loss, and which water travels uh, at the second through the second pipes. It gets more tired and tired, and as soon as it just exit, you have to subtract all those head losses due to the water tiredness over this travel distance, and that's our head loss. Let's see our head losses. So let's have a closer look to know how we can calculate our head loss. So for the first part, we can have like our length of our first pipe times the friction head loss, which is a coefficient of a 3%. So that's that length time that coefficient plus the contraction plus the same terms for the second pipe, 350 feet times 5%. And if you add them up, it just gives you the total head losses due to contractions, change of diameter at here, and also which water travels from A to B, then B to C. The overall of that is 39.5 feet of head losses. So if we just get our head loss, goes back to our equation, we already know a 1 psi is equal to 2.31 feet of water. We already have P at A, pressure at A is 80 psi, so simply multiply that by 2.35, 31, then plus our head loss is already calculated from the previous part. We have it here, and also V1 squared over 2g, and this is the g in US customary velocity at point A is 10 feet per second. The squared over 2g minus the head losses is equal to v squared, v2 squared over 2g. The only unknown in this equation is velocity at point 2, which is what we are looking in this example, and that's gives us the answer is choice D. So it was kind of a comprehensive calculation of pipes hydraulics in a simple test, which includes the head losses and also application of Bernoulli's in two pipes in series. Thank you. We'll solve more problems in pipes.